Hello everybody and welcome back to episode 50 of the video series in which we program an entire video game from scratch, from beginning to end in the C programming language. No engines, no libraries, just our own brains. So this is episode 50, so it's quite a milestone. Last time, actually before we get into what we were doing last time, let's look at some viewer comments. Okay, first commenter says, "Hey Ryan, I'm thinking ahead about a good approach for saving game data. Are you planning to write a custom format, or might you consider using something like SQLite as your game state file format?" That's a good question. Honestly, I have not spent 1 minute thinking about saving games just yet. I know that it's something that I will definitely need in the future, but it's not something that I have put any thought into at all. That being said, I'm familiar with SQLite, but um, I'm not sure if there's really any need to use it. I feel like when it comes time to save a game, I will probably just need to collect some, key pieces of information. I'll have basically like information about your player, like their world position, what their experience level, how much gold they have, it's et cetera, et cetera. All the statistics about your player, and then I need a list of like all of their accomplishments. Like what all have you accomplished? Like have you collected the hammer of Cloud City? Have you slayed the dragon of Far Reach or whatever? All these things. Have you done this? Have you done that? Have you done this? Have you done that? And based on whether those events have passed or not, that will basically set the world back the way that it's supposed to be so that you can pick up where you left off. That is just my off the top of my head thinking as far as what we'll do for game state. I have no idea if it's going to work or not. I've never put it into practice, so we're just going to have to wait and see what happens when we get there. As for storing that information using SQLite, I'm familiar with SQLite and it would be perfectly fine to use it, but I don't know that we need to at this point. So I think we have kept the number of third party things that we're going to be using in this game to a minimum. We didn't roll our own audio library. We're using Xaudio 2. Like, we did write our own functions to load wave files, and we load those files from the disk, but we're just feeding those into Xaudio 2 to play them. It's more or less just a black box API. So that's a third party thing. That's one third party thing that we have. We're using X input to do um, gamepad input. That's a third party thing that we have. But other than that, most of this stuff is ours. And I feel like considering that this video series is supposed to be mostly our own handcrafted stuff, as much as possible. Not 100%, but as much as possible. Oh, and we also use a third party thing for compressed zip files, and a third party thing for decoding Og Vorbis. But that's it. Other than that, it's all us. Um, so that being said, I don't really mind using SQLite, but I don't think we need to. I think that if we just make the save game, if we collect all that save game data, like I was just talking about, write it into a file, and then save that file into a compressed archive using the same archive compression function that we already have, I think that will effectively like discourage people from going in there and hacking their save game file, to give themselves like a million gold or whatever. Now, people are still going to be able to do it, but it's not going to be as easy to do because remember, like this assets.dat file, we're saving that using um, some of the facilities provided to us with miniz.h or miniz essentially. But we purposely went in there and changed some of the file headers, some of the signatures, so that normal tools won't be able to read it. So, for example, if I right click on assets.dat and I try to open it with 7-zip, you'll notice that 7-zip does not recognize it as a regular like zlib or zip file type archive, right? And the same thing if I were to rename it to .zip and I try to open it with Windows Explorer, you have the same problem. Windows Explorer cannot open the zip file either. Even though the file format is practically identical, we just changed some of the signatures, file headers, basically some of the metadata, so that regular tools couldn't recognize the file format. So it's kind of cheesy, I realize it's not going to make it hack proof, but it is going to make it, tamper resistant to like the average player. So, and especially since this is an open source game, obviously I realize people are going to be able to go and look at the source code and see exactly, how to open this type of file. But I'm just saying, to the average player, they're not going to invest, they're not going to do what needs to be done to figure out how to reverse engineer this file format so that they can then get the data out of it and modify it. So yeah, that is my take on that. Let's go to the next comment. The next comment says, "Hi Ryan, wondering if this brick tile would be helpful for you, even just as just a template. Cheers." Okay, let's click on it. Load. There it goes. Okay, so opengameart.org, and there is the preview of the brick tile. And yes, that is exactly what I was trying to do in the last episode, and I failed miserably because I really don't know anything about tile editing or pixel art. I'm really just flying by the seat of my pants here. So maps, bricks01. Let's see what it looks like. Edit with paint.net. And since it's just a 16 by 16 tile, what is the problem here? There we go. Take this color, this color. I don't know if, I think it's light on dark, dark on light. It doesn't really matter. Okay, so this one's colored. And then it looks like he goes up 3. Skip 3, like that. 1, 2, 3. 1, 2, 3. And then, yeah, that will work because we've got 3 pixels here, 1, 2, 3, and then the bottom pixel of the tile above it will have this the grout, essentially. So yeah, we're on the right track. There we go. There we go. All right, how many pixels do we think that is? Skip 2 over here. 1, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Something like that. And then there. Okay, so do you think that is an accurate replica? Save, save. That looks much better. That looks much better. Remember last time it was like not, like it didn't tile correctly because of the way that I drew it. I didn't draw it correctly, so it didn't tile correctly. But this time, it looks much better. And so thank you for showing me that. That will definitely come in handy because I'm going to be making dozens more different types of tiles in the future. By the way, these other sorts of tiles that are like, these are still pretty ugly too, and I will definitely have to prettify, make these prettier in the future. Um, but I just wanted to get something out. And, I had to make two different types here to sort of give a three-dimensional effect, right? So let me export as image, PNG, export, close, open, PNG, save as, BMPX, save, save, close, run copy assets.bat to rebuild our assets file. Finally, run the game. And let's see what it looks like. There we go. That looks better. Okay, awesome. What do I want this episode to be about, though? I actually have something in mind, something that we need to finish. And that is our vectorization. Now, I've done probably, I think this will be the fourth episode on vectorization, and it may actually be the last episode on vectorization. Because once we get this, the rest of this pixel blitting code vectorized, then that's pretty much the only performance intensive, that's the only thing that we do that's even remotely performance intensive. So that's really the only thing we have to vectorize. And by the way, vectorization, which I don't often use that term, it simply means to convert your code such that it uses the SIMD, single instruction multiple data intrinsics, as opposed to just your classic, C type stuff that we've been using. So we've already vectorized blit background to buffer, and the reason why blit background to buffer and blit 32-bit per pixel bitmap to buffer are separate functions is because blit background to buffer I knew was going to be much easier to vectorize. And how did I know that? It's because I know for a fact, based on our game's rendering resolution, which is width times height, so 384 by 240. That basically means that our resolution is always going to be in a multiple of both 4 and 8. So if I'm using AVX2, which in fact I should change this pound define to AVX2. Okay, I take that back. I'm wrong. Okay, AVX instructions support both 128-bit and 256-bit SIMD. 128-bit versions can be useful to improve old code without needing to widen the vectorization. Okay, so both AVX and AVX2 both had 256 bit wide registers, so that's fine. I don't know why, for some reason, I was thinking that the 256 bit registers didn't come along until AVX2, but erase that from your mind. That is incorrect. So back to what I was actually talking about. The reason why I wrote Blit background to buffer separately is because I knew that based on our resolution of 384 by 240, that this thing, this game bitmap, which is our background, the amount of rendering that we're going to do in this function is always going to be in a multiple of either 4 or 8. And with AVX, remember we have 256-bit register, we can fit 8 pixels in there. And with SSE2, we have 128-bit registers, we can fit 4 pixels at a time in those registers. So and because I can reliably say that I always know that it's going to be a multiple of 4, I can just, I can just write this code knowing that I'm never going to, I'm never going to have a remainder here, right? Like, this is always going to exactly match the background that I'm drawing. It's always going to, the math is always going to work out. With Blit 32 bits per pixel bitmap to buffer, on the other hand, that is not the case. And the reason it's not the case is because we don't know how wide the bitmap that we're going to draw is. We don't know if this bitmap is going to be a multiple of 4 or a multiple of 8 or even an even number. We don't know. It could be odd number. It could be a 7 by 7 thing that I want to draw. Now, if I'm drawing a 7 by 7 bitmap, that makes this logic a little weirder because I can no longer just say, I can no longer just increment x pixel by 8 because that 8th pixel is not part of the bitmap. And I'm going to get some pretty weird effects and crashes if I do it like that, I think. So let me draw something to illustrate what I'm talking about. What is this? Ascii Flow. Yeah, so let's say this is our screen right here, and I want to draw, I want to draw a string that says, uh, today is a good day to die. How many? That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's just say however many characters it is. Let's say that it comes out to be, how many pixels wide are each of our characters, right? They're like 6 pixels wide. Each character is 6 pixels wide. Yeah. And then let's say we have a string that's like 10 characters long. So 60 is not a multiple of 8. It is a multiple of 4. We'll say it's 61 pixels. Or wait, I bet we could keep doing this until we find one that's, say, if it's 11 characters long, 66 pixels is no longer a multiple of 4 or 8. So yeah, we're going to, if we wanted to print out an 11 character string, it would be 66 pixels long, and it would not be a multiple. It wouldn't be an even multiple of either 4 or 8. So our SIMD code, as it is right now, wouldn't work. So it's time to fix that. And first, before we start, I want to get a little bit of a baseline here. Okay, so I walked over until the FPS raw figure was just off of the water and in the grass because that makes it easier for me to read. And looks like we're pulling at about 1100 frames per second. About maybe 1050, 1100, something like that, which is pretty good. But I think we can make it even better if we finish vectorizing this. Um, so how are we going to do that? So here's my thought right off the bat is visualize again, if you will, our string, which remember our string is like a string bitmap. If you go to Blit32BppBitmapToBuffer, remember we have this function that creates a string in a separate bitmap, and then it draws that new temporary string bitmap using Blit32BppBitmapToBuffer, right? So visualize, if you will, that our string bitmap is an 11 character long string. So if it's 11 characters long, it's 66 pixels. So my thought is this: what if I go back to Blit32BppBitmapToBuffer? Notice I have these nested for loops that basically just loop through each pixel in the bitmap one at a time. If I did this in a SIMD fashion, I would do like iterate through 8x pixels at a time, because with AVX or AVX2, I'm going to pick up 8 pixels out of the string bitmap, and then I'm going to drop 8 pixels into the back buffer at once, right? But I can only do that once, because if I did it twice, then it would be uh, how many? Let's see how many times can I do that? Knowing that this string bitmap is 66 pixels, I would only be able to do it 8 times, right? Because 8 times 8 is 64. But then I have like these two dangling pixels on the edge of the row, on the end of the row, right? Every row would have these two dangling pixels where I need to draw them individually. So that's my thinking. Let me draw it again, because I don't know if this concept is as clear to you as it is in my own head. So let's say that this is our big string bitmap, right? And it's got like 11 characters in it. 1, 2, 3, 4, 5, 6, 7. Don't worry that they're not exactly the same width. Just pretend that they're the same width. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's our string bitmap, right? Now with AVX, I can draw by looping through 8 groups of 8 pixels. I can draw all the way up until like right here, right? So I can draw like all of these pixels right here, right? Right there. So it's going like halfway through the last character. But then I've got like these two dangling pixels left over here on the edge. I can't do another group of 8 pixels, because that would put me somewhere off here to the right of string bitmap, and that's just like undefined memory space that I can't touch, right? Or it's like an offset of the bitmap that doesn't make any sense. I think it would probably actually write. It would probably start writing some of the stuff from the left of the bitmap and put it like over here or something like that. It wouldn't work. It would be strange. So my thought is, let's just loop by 8 at a time. Let's go 8 by 8 pixels at a time until we get to the very end here, and then we'll just finish off each row 1 pixel at a time, just like we have been doing. That exact same logic applies to SSE2 as well, except we'll just go by groups of 4 instead of by groups of 8, which you've seen me do in previous episodes. So, all right, let's get started. And the first thing I'm going to do is get rid of all this junk. I really hate this stuff. This right here, I wrote this in a hurry, thinking that like I really want to prevent myself from attempting to draw pixels off the screen, because it never does what you want to do. It either creates that wraparound effect, like when you're playing Pac-Man and you go off one end of the screen and you scroll right back into the other end of the screen. Or if you happen to be off on one of the like top edge or bottom edge, it will crash the game entirely because you'll be trying to deal with memory that's not even within like the back buffer memory, right? So, the reason I hate this is because it's ugly and it's probably not even correct. And I think you've heard me say many times that when you're dealing with code that you want to be really hot, and perform as fast as possible, the practically the number one thing that you want to do is eliminate branching code paths. And branching is whenever you see a whole bunch of if statements like this, there's so many different branches that the code could follow. That's what you want to eliminate from your code, if at all possible. But that being said, the real reason I want to get rid of this, it's not really the number one reason I want to get rid of this is not because of performance reasons. It's because I don't even think it's correct, and it's inelegant, and I don't like it. So for the time being, I'm just going to get rid of it, and I'm going to basically just make more of an effort to just not draw pixels outside of the viewable screen area. And I'll just have to trust myself in other parts of the code right now to just not do that. All right, so let's go ahead and do our usual if def avx thing, and then else if defined SSE2, and finally else, which is like if neither avx or SSE2 is defined, then we're going to do it just like we were doing it before. This is the old-fashioned way. And we'll do end if right there. Okay, so now this is our original code that does it one pixel at a time. Our original code is now if def out. I want to work on this avx code. And first thing I want to do is I want to make an M256i, which is going to be my bitmap octopixel. And of course you remember this from, the last time we did this. It's just this guy. And in fact, we can go ahead and just copy these things too. In fact, we can copy... Actually, I don't think we can. I think we could copy this one. This outside for the Y pixel, the rows. There we go. And the reason why I'm defining this here is because I think in this code path I'm going to have to use both. I'm going to have to use both bitmap octopixel, and then when I reach the end of the number, however many loops of 8 pixels at a time that I can do, then I have to finish the remainder of the row with the regular bitmap pixel one at a time. Okay, starting those the same, starting screen pixels the same, starting bitmap pixels the same, memory offset, bitmap pixel, my octo pixel. However, now I don't think I can use the inner for loop. I think I need a different kind of loop. I think I'm going to do something like this. Int 16 pixels remaining on this row. And it's going to be initialized to the width of the bitmap that we're drawing. And I guess we still need an X pixel, and it starts at 0. And then we're going to do a while loop instead of a for loop. We're going to do while pixels remaining on this row is greater than or equal to 8. So while pixels remaining on this row is greater than or equal to 8, we can continue doing our AVX style stuff. And we're going to do, actually at the end, we're going to pixels remaining, we're going to decrement this by 8, and we're going to increment X pixel by 8. I don't know why I insist, my finger somehow insists on typing a 9 when I'm trying to type an 8. Okay, and then we're going to do another while loop. While pixels remaining is greater than 0. We're going to do our standard like non-SIMD style that we've already done to finish off the row. So this while loop should theoretically run, somewhere between 0 and 7 times, which that should effectively save us some time overall drawing this thing. Let's go ahead and copy all of this and put it here. And remember, what we're doing here is we're not actually doing alpha blending. This is not proper alpha blending, and I hope that the decision to not do alpha blending doesn't come back and bite me in the butt later on. But what we're doing right now is we're simply only drawing pixels that are opaque. We're only drawing pixels that have an alpha channel of exactly 255. Those are the only pixels that we're drawing. And remember, we have to clamp, because of the brightness adjustment value, we have to clamp each result between 0 and 255 so that there's no wraparound. Right? Because I can't make a pixel brighter than 255 and I can't make a pixel darker than 0. Alright, so that's my non-SIMD. So if I ran the code right now, what I anticipate would happen is that you wouldn't see any of the bitmaps on the screen except for maybe the ones that were not exact multiples of 8. You would see just a couple of pixels on the right-hand side from where I'm doing the remainder, the stuff that couldn't be vectorized. Okay, so we need to make sure and increment these things. We forgot to increment these things. We need to do pixels remaining on this row -1 and x pixel +1. We got ourselves into an infinite loop there. Yeah. So there you have it. We're drawing only the parts. We're drawing only the parts that are not multiples of 8. Like we're drawing the remainder of each row of text over here, which is why you only see some garbage over here. All of this stuff that's not being drawn is the stuff that is a multiple of 8 that can be vectorized. So let's do the vectorization. Most of this we've already done before. Let's see how much time we have. All right, we have 20 minutes. So I think we can finish this. Let me make sure that my OBS is still working correctly. Most of this vectorization we've already done before. So let's do memory offset and bitmap offset are calculated the same way in both vectorized and non-vectorized versions. We need, this is where we load our bitmap octopixel, which is going to be, I'm going to go down here to blit background to buffer. I think I can copy most of this stuff. Yeah, I think I can copy most of this straight out of blit background to buffer. So let me go ahead and do that, and I'll modify it when I need, as I need. Here we go. I'll just plop it in right here. Okay, so first thing, we load 256 bits from game bitmap memory plus offset into octopixel. That's going to populate our 256-bit YMM register with 8 pixels. Now remember, we have to add the brightness adjustment, and it's important to me. It's important that I don't get into a situation where the pixels are drawn differently or behave differently depending on whether I do vectorized code or non-vectorized code. That's my number one priority, is that I want the pixels to behave identically regardless of whether I'm using vectorized code or non-vectorized code. What do I mean by that? Is that I don't want like the fading effect to behave any differently, whether I'm doing it 1 pixel at a time or 8 pixels at a time. So that part is really important to me. Now, if you'll recall, we have to add in the brightness adjustment, and the brightness adjustment is a 16-bit integer. And the reason it's a 16-bit integer is because I explained this a few episodes ago. I want to be able to, if I have a 250, if I have a white pixel, imagine a white pixel has a red, a green, and a blue component, all 255. Full red, full green, full blue. I want to have the ability, if I so choose, to turn that white pixel into a black pixel using the brightness adjustment. So if I give it a brightness adjustment of -255 here, then it will take that white pixel and it will add -255 to each the red, green, and blue components, pulling all of those values down to 0. Then I will have turned my pixel that was originally white into black. Also, this works vice versa. I can turn a black pixel into a white pixel, and I can go anywhere in between. That's why this needs to be a 16-bit integer instead of an 8-bit integer, because an 8-bit integer If it's unsigned, then I won't know whether I mean to add to it or take away from it, because it's unsigned, right? I can't have negative numbers in an unsigned integer. If it's a signed 8-bit integer, I could only fit a maximum of it. It only goes from negative 127 to positive 127. So there's no way I could subtract 255 from it, because that's not a number that I can express in a signed 8-bit integer. So that's why this needs to be 16 bits. The problem that introduces is that how do you add 16 bits? How do you add a 16-bit number to an 8-bit number when they're all packed together in this register like this? The answer is you blow this apart into multiple halves. So that's why, and again, I explained this in a couple episodes ago, but I'm just kind of rehashing it a little bit here. I'm taking my 256-bit register, breaking it apart into two 256-bit registers. I'm zero extending every one of these color channels. So now an alpha value of FF is now expanded to 00FF. That converts it from 8-bit to 16-bit, which is exactly what these functions are for. What I'm doing first is I'm extracting the first 128 bits from bitmap octopixel. So I'm taking half of bitmap octopixel, that's 4 pixels. I'm blowing it apart, stretching it out so that now each color component is 16 bits instead of 8 bits. Second thing I do, now that each color component is 16 bits, I can now add a 16-bit integer to each component, right? So what is that? What is the number that I want to add to it? It's my brightness adjustment. So I'm going along here and I'm adding the brightness adjustment to each one of these 16-bit components, 16 bits at a time, right? Well, actually, it's doing the whole 256-bit register at once, and that's why it's faster, because I'm operating on 8 pixels. Well, right here I'm operating on 4 pixels at a time instead of 8 pixels, instead of 1 pixel at a time. So, for example, you can see here that I started with an alpha channel. You can see here that I started with an alpha channel of FF, which is 255. My brightness adjustment, which starts as negative 255, because remember I wanted to fade in from black. So after adding negative 255 to it, becomes 0, right? And subsequently all this other stuff, these are like negative numbers, these ones that start with F. Now I'm already starting to see the problem with this code. This code worked perfectly fine for the background, right? I copied it out of the blit background to buffer function. This worked perfectly fine for the background, because remember, blitting the background doesn't matter what the alpha channel is. The alpha channel is completely disregarded. GDI doesn't care what the alpha channel is. It only cares what the RGB, the color data is, right? This does not work for blit 32 bits per pixel, however, because remember, I'm taking advantage of the alpha channel myself to create transparency. I need the alpha channel. So what this means is this isn't going to work. And the reason why this isn't going to work is because I need a way to manipulate every color with the brightness adjustment except for the alpha channel. I need the alpha channel right here. I need the alpha channel to stay at 255. Like if it was already at 255, I need it to stay at 255, because if I don't, I won't be able to. it's either going to be opaque and it's going to draw like it's gonna draw like stuff where it shouldn't be drawing, or in the case of like where I've taken all of the alpha channel, I've taken it down to 0, it's not going to draw it at all. Like this doesn't account for opacity, so I need to fix this. All right, good news is I think it's pretty easy to fix. So here's half one. I'm adding the brightness adjustment to it. I can just change this piece right here. See, this is just taking, this is setting one 256-bit register to all, like it's setting every component to brightness adjustment. But what if instead I did something like this? Actually, literally just take away this 1 right here. And that will allow me to set each component individually. Each 16-bit component separately. So A, R, B, G, A, R, B, G, A, R, B, G, A, R, B, G. So now I'm saying, by doing it this way, I'm saying I want you to add brightness adjustment to every component except for this alpha component. And by leaving the alpha component here at 0, I'm simply saying don't do anything to the alpha component. Only manipulate the RGB half of it. In fact, before I do this, I want you to see what this looks like before I do it this way. Let's see if are we ready to go? I think this should work. Let's see if it compiles. Let's see if it runs. Let's see what it looks like. Okay, that looks fine. Okay. So what do we have? Like, what do we have here? Basically, what we have here is, notice our character. First of all, our character we know is 16 by 16. That's a multiple of 8. So we know that he is completely vectorized. However, notice that he no longer has a transparent border around him. It drew everything as white all the way around him. We have these number 1s adjacent to the player, all around the player, to show the tile values. Those are completely non-vectorized because the size of these bitmaps are less than 8. So there's no vectorization going on with the number 1s. And that means the transparency code is still working correctly. Now shift your focus over to the debug text. This is interesting. You'll see that the transparency is gone. It's now drawing white on black instead of white on transparent. But also notice that it looks like our original idea of drawing the row all the way up in groups of 8 until we can no longer draw in groups of 8 anymore, and then we just finish off the remainder of each line of the remainder of each row in pixel by pixel non-vectorized style, right? So that part I think is working correctly, because as you can see, everywhere where there's a black background, that's where the vectorized code is running. And then when we run out of room and we can no longer do it in a vectorized fashion, we take over pixel by pixel. We finish off the row pixel by pixel, and that's where the transparency is working. So you've got this weird sort of situation where, you know, the black bar is like almost up to the edge, and then just like the last few pixels have transparency underneath them. Needless to say, that's not what we want. So let's redo what I was just talking about. I think it's Control Y. Should we see? Yeah, Control Y is the opposite of Control Z, is redo. Okay, so now here's my this is my 4 pixels in a 256-bit register, and now I'm saying I want to take that brightness adjustment, and I want you to just manipulate the RGB. I want you to leave alpha channel alone. Okay. Now we need to do the same thing. We need to do the exact same thing for the second half. So as you can see, I'm extracting the second half of bitmap octopixel using this index right here. See, this index of 0 means extract the first half. This index of 1 means extract the second half. Then with this function, I'm blowing it out. I'm 0 extending all of the components from packed 8-bit integers to 16-bit. Now I can do my arithmetic. I need to do the same thing here. This will be identical. ARGB. There we go. Half 1 and half 2. And then we have, now we need to take our 2 halves and we need to recombine them basically by packing them back into, each component needs to be repacked from being 16 bits wide to being 8 bits wide. And then this function, remember, since it uses unsigned saturation, it automatically does the clamping for us, so we don't need to do any of our own clamping. So you remember this stuff right here in our non-vectorized code where we're having to clamp between 0 and 255. We don't have to. This function does it for us, so we're going to let that happen. And then because this function, for some reason that I don't understand, repacks them into it interleaves them into an order that into a weird order for some reason. I have to reorder them myself. So that's what the permute function is for. Is basically I need to just take these. I need to take this 256-bit register, divide it up into 64-bit components, shuffle them around so that the third 64 bits go first, and then the first 64 bits go next, and then the second 64 bits go third, and then the first 64 bits go all the way to the other side. Finally, that's recombined in the right order. So now, let's see what it looks like. Ah, interesting. It didn't work. Why didn't it work? It didn't work why didn't it work? That's a very good question. Oh, I know. Here's why it didn't work. It didn't work because this function right here, mm256 store Ascii 256, it's unconditionally storing 8 pixels of data, 8 pixels worth of data directly from the bitmap to the back buffer. There's no logic in here to say only transfer the pixels that have an alpha value of 255. Remember, down here in the non-vectorized version, we can do this manually by checking the alpha component of each pixel. Say, hey, if it's 255, then I want you to go ahead and transfer it. But if the alpha value of the pixel is not 255, it does not get transferred to the back buffer at all in any fashion. So we need to come up with a way of doing that here in the vectorized version. Um, we can do that. In order to do that, we need to make a mask. So here's the cool thing, and this is kind of like the capstone on our SIMD project, if you will, because there are two things about SIMD that make it super fast. Obviously, the first and most obvious thing that makes SIMD generally faster at crunching lots of data is that we can manipulate large chunks of data with single instruction, multiple data intrinsics. You know, we can work on 8 pixels simultaneously instead of doing them one at a time. But there's another benefit to SIMD, and that is you can perform branchless conditional operations. Remember, earlier on I said, and I've said this multiple times throughout this video series, if you're trying to write the fastest code possible, avoid branching. Of course, you quickly come to realize that it's kind of difficult to do a lot of stuff in C if you don't have conditionals. Like if you can't use if statements or switch case, if you can't do that, like you kind of can't do much. That's where that's where this beautiful power of SIMD. This SIMD has this beautiful power of creating a branchless conditional. So I'm going to try to explain this the best I can. First, I'm going to create a bit mask essentially, and I'm going to store it in a 256-bit register. So M256I, and I'm just going to call it mask. This mask is going to be comprised of, it's going to basically, how am I trying to say this? I want to take a look at bitmap octopixel, and I want to create a mask based on which pixels in bitmap octopixel have their alpha value set to 255. That's what I want to do. That's what I want you to do. I want to create a mask so that I know which pixels within bitmap octopixel have their alpha channel set to 255. So to do that, let's see, MM256. Okay, so there's a compare equal EPI8, which is just 8 bits. Bitmap octopixel, and then we need to compare it with something. So MM256 set 1 EPI8 -1. Let me go to the intrinsics guide. Select AVX and AVX2. Okay, MM256 compare equal. Here it is. Compare 8-bit integers in A and B for equality and store the results in destination. So essentially, I'm comparing using these two things, and this right here. So you could do this multiple different ways. The reason I'm using this is because -1 is essentially conveniently, basically sets that high bit for us, right? So it's like 0xf, and it's looking for that alpha channel of like f. There's multiple ways you could do it though. for example, instead of this, I could have actually also done, let's see, MM256 set1 EPI32, and then I could have expressed the entire, basically an entire pixel right here. So like FF, saying, let's see, FF RGB, right? So there's your whole pixel, and then this is the alpha channel right here, right? Okay. Now I'm going to set a breakpoint right here, and I'm going to see what happens. When we create that mask, I want to look at my disassembly. Okay, so essentially what I'm trying to do here is I'm trying to decide which is cheaper. Oh yeah, I can't, there's no copy there. I hit that. Okay. All right, now let me stop the program and let me replace this with EPI8 -1. Now, I think it will essentially have the same effect, but let me run it and see what happens. Okay, it's identical. Sorry, I was hoping to show something cool here. I thought that these were going to generate different different sets of instructions, and I was going to show you why this one was actually cheaper. But it looks to me like this one is actually, it looks like they produce identical disassembly, so it doesn't matter. Okay, back on task here. Back on task. Okay, so now we've created our bit mask. We've created our mask. Now instead of storing, just unconditionally storing the results like that, I'm going to use another intrinsic called mask store. 256 mask store, EPI32. And this takes, basically it takes a memory address, same as before. So it's going to be this guy right here. And then it takes a mask, which is that guy, mask, we've already made it. And then we need the thing to apply the mask to, which is bitmap octopixel. Now the results of this is that it's not going, the results of this is that it's only going to move the pixels where the alpha channel is set to 255 because of the bit mask that we created. This should give us back our transparency. So let me take away all our breakpoints and try it again. There you have it. We walk over here. Okay, so it looks like now our FPS, what did we start? We started at 1050 to 1100 FPS at the beginning of this episode, and now after vectorization, you can see that we're up to 16 to 1700 FPS. So a clear win there, and you can see that our transparency is still working perfectly fine. You can see that our our fading. If you notice closely, the fading. Remember the fading on the background and the fading on the our character is done separately. But if you focus carefully on the character, you can see that the fading in from black on him is working perfectly as well. So everything is working, and importantly, this is really important to me, is that it's pixel perfect, the same behavior, regardless of whether we're using vectorized or non-vectorized code. Whew, so we got done with that. Now, the next piece of the puzzle is we need to replicate the exact same thing in SSE2, which I don't have time to do today because we're already over time. But I will say that it's going to be identical, not identical, but it's going to be very similar to this code that we just wrote today. Only we're going to be going 4 pixels at a time instead of 8 pixels at a time. Now, and remember, the reason for me breaking it out like this is just in case maybe someday we need to run this code on a really old processor that doesn't have AVX or AVX2. It's just, it's just something that I wanted to do. I will say that this code that we wrote today, I'm not promising that it is the fastest possible way that this could have been done. Someone smarter than me may figure out how to speed this up even more, but this is the best that I could come up with. And I'm happy that at least it's an improvement over what we had. So it's not like I did any harm. I did make it faster. So if anybody can think of a way to make this even faster than it already is, be my guest. I would love to see it, but this is the best I could come up with. I will say that I have heard that Mask Store is really slow on AMD hardware specifically. It's efficient on Intel chips, but it's actually much slower on AMD chips. And that's unfortunate because I didn't want to get into a situation where I'm writing code differently just for different brands of processors. That's not really what I want this channel to be all about. Like, this is the most this SIMD stuff I think is going to be the most processor specific, or CPU specific stuff that we're ever going to write on this video channel. But anyway, that being said, I'm going to leave it just because I don't have an AMD processor to test it on. I only have an Intel processor to test it on. So if one of you out there has an AMD processor, if you could please tell me, test this code. Tell me what your results are. What kind of FPS you're getting. That would be awesome. But other than that, I guess that's all we have for today. And with that being said, I can blow this to do away because we're done with that. It's now vectorized. Cool. Okay, so I'm going to call it for today. And as always, thank you very much for watching. If you liked what you saw today, you want to watch me continue developing this game, please hit like on the video, hit subscribe on the channel, and tell your friends. Also, don't forget, if you have any questions or comments on any episode, on any of the material covered on this video series, don't hesitate to leave your comments on the video. I'll address any interesting questions or comments in an upcoming video. Lastly, don't forget that we have a companion GitHub repository that I keep updated in step with these videos, if you want to clone that GitHub repository so that you can follow along at home. That's all I have for today. Thank you, and see you again in a few days. Bye.